Gravity is one of the fundamental forces of nature, a force that attracts objects with mass toward one another. It's responsible for many phenomena, from the motion of planets in their orbits to the behavior of objects we see and interact with every day. Despite being a familiar and essential part of our lives, the way gravity works is actually quite profound and deeply rooted in the fabric of the universe. Let's explore how gravity works, both from a classical Newtonian perspective and a modern Einsteinian perspective. Newtonian gravity, the classical view. In the 17th century, Sir Isaac Newton formulated the first comprehensive theory of gravity. According to Newton's law of universal gravitation, every mass in the universe attracts every other mass with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This law describes how two objects exert a force on each other due to their masses. The larger the mass of an object, the stronger the gravitational force it exerts. Similarly, the farther apart the objects are, the weaker the gravitational pull between them. For example, the Earth exerts a gravitational pull on object, which is why things fall to the ground when dropped. Likewise, the Moon's gravity causes the tides on Earth. The Sun's massive gravitational pull keeps the planets in orbit around it. What is gravity? Newton described gravity as a force, but he did not explain what that force actually was. He was more concerned with how it worked and could be calculated. In the 19th century, scientists began to think about gravity in terms of fields. A gravitational field is a region of space around a mass where other masses will experience a force due to gravity. In this framework, you can think of the Earth as creating a gravitational field that extends outward from it. Any object placed in this field will feel the force of gravity pulling it toward the Earth, which is why objects fall when dropped. This force diminishes with distance, but it always extends outward, theoretically, to infinity. Einstein's general theory of relativity, the modern view. In the early 20th century, Albert Einstein revolutionized our understanding of gravity with his general theory of relativity. While Newton's theory worked very well for most situations, Einstein showed that it wasn't complete, especially in extreme conditions, such as when dealing with very massive objects, like black holes, or very high velocities, near the speed of light. Einstein's key insight was that gravity is not a force in the traditional sense, but rather a result of the curvature of space and time, known as spacetime. According to his theory, massive objects, like the Earth or the Sun, warp or curve the spacetime around them. This curvature tells other objects how to move. Essentially, objects follow the straightest paths in curved spacetime, but since spacetime is curved, these straight paths may appear curved from the perspective of an observer in flat space. A famous analogy to understand this concept is imagining a heavy ball placed on a trampoline. The ball causes the trampoline to sag and curve around it. If you roll a smaller ball on the surface of the trampoline, it will follow a curved path, influenced by the curvature caused by the heavier ball. Similarly, the Earth curves spacetime, and the Moon follows a curved path around Earth due to this curvature. To put it simply, gravity isn't pulling objects in the way we think of forces. Instead, objects are simply moving along the curved paths dictated by spacetime's geometry. How does gravity affect time? One of the most fascinating consequences of Einstein's theory of relativity is the idea that gravity can affect time itself. This is known as gravitational time dilation. The stronger the gravitational field, the slower time passes relative to regions with weaker gravity. For instance, clocks on the surface of the Earth run slower than clocks in orbit or at higher altitudes. This effect is very small, but it's real. For example, GPS satellites orbit the Earth at higher altitudes and experience weaker gravitational fields than clocks on Earth's surface. If their time measurements weren't adjusted for this difference, the system would give incorrect location data. Gravitational waves, ripples in spacetime. In the 20th century, another groundbreaking aspect of gravity emerged from Einstein's predictions: gravitational waves. These are ripples in spacetime that propagate outward from massive accelerating objects, such as when two black holes merge. Gravitational waves are similar to how ripples spread across the surface of water when you throw a stone into it. But instead of traveling through water, gravitational waves travel through spacetime itself. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting gravitational waves for the first time, confirming yet another aspect of Einstein's theory. These waves provide a new way of observing the universe and can offer insights into phenomena like black holes, neutron stars, and other extreme cosmic events. Dark matter and dark energy. The mysterious side of gravity. While we have a good understanding of how gravity works, there's still a lot about it that remains mysterious. One of the biggest challenges in modern physics is the concept of dark matter and dark energy. Observations of galaxies and galaxy clusters suggest that there is much more mass in the universe than we can detect with our telescopes, and this invisible mass is exerting gravitational effects. This invisible matter is called dark matter. Moreover, the expansion of the universe is accelerating, which suggests there is a form of energy, dubbed dark energy, that is causing space itself to expand more rapidly. These phenomena do not seem to be fully explained by our current understanding of gravity and the laws of physics, and they represent some of the most profound unsolved mysteries in cosmology. Gravity on Earth. Everyday experiences. In our everyday experience, gravity is the force that keeps us tethered to the Earth. It's responsible for objects falling when dropped and for our weight. The force of gravity is what holds everything in place, from the oceans and atmosphere to the buildings and trees around us. The acceleration due to gravity on Earth's surface is approximately 9.8 meters per second squared, ms superscript 2, meaning that any object, regardless of its mass, will fall at this rate, neglecting air resistance. The force of gravity is also what makes life on Earth possible. It keeps the atmosphere in place, holds water in our oceans, and ensures that the Earth's conditions remain stable. Without gravity, life as we know it wouldn't be possible.